So, esteemed Professor Zeilinger, dear Madam Zeilinger, Your Excellency, the Ambassador of the Republic of Austria, Mr. Bühler, spoštovane članice in člani Slovenske akademije znanosti in umetnosti, spoštovani gostje, spoštovane gospe in spoštovani gospodje. Za današnjim slavnostnim predavanjem Nobelovega nagrajenca in našega dopisnega člana, profesorja Antona Zeilingerja, praznujemo dan Slovenske akademije znanosti in umetnosti. Z njim se spominjamo ustanovitve naše akademije, ko so se na današnji dan, 12. novembra 1938, na prvi skupščini sestali njeni ustanovni člani. S tem dejanjem je bila akademija, ki je bila formalno sicer ustanovljena nekoliko prej, za uredbo tedanje jugoslovanske kraljeve vlade v Beogradu, tudi dejansko priklicana v življenje in je začela z delom. Slovenska akademija znanosti in umetnosti praznuje letos 86 let od svoje ustanovitve, s čimer ne sodi niti med najstarejše, niti med najmlajše akademije v Evropi in v svetu. A obenem se naša akademija razume tudi kot naslednica Akademije delavnih, Akademije Operozorum, prve akademije na Slovenskem, ustanovljene leta 1693 v Ljubljani. Letos bi bila stara že več kot 330 let, vendar je že po nekaj desetletjih prenehala delovati. Njeni člani, kranjski in ljubljanski pravniki, zdravniki in teologi so si za svoje geslo izbrali besede nobis atque alis in ga v svojem grbu povezali s čebelami, prispodobo marljivega nabiranja znanja, ki se nalaga v panjo kot simbolu hrama modrosti in s katerim se na koncu sladkajo vsi. Geslo operozov, da je njihovo delo namenjeno oži, to je domači, v našem primeru slovenski skupnosti in v splošno korist, je tako brezčasno in univerzalno, da je tudi temelj dela Slovenske akademije znanosti in umetnosti. In v tem smislu se tudi smatramo za naslednike Akademije Operozov, o čemer zgovorno priča njen grb, ki krasi našo akademijsko dvorano, čeprav seveda med obema akademijama ni neposredne povezave. Dan Slovenske akademije znanosti in umetnosti smo uvedli leta 2022 in ga letos praznujemo tretjič. Z njim se želimo poudarjeno spominjati začetkov naše akademije in tudi na takšen način v slovenski javnosti krepiti zavest o njenem pomenu za Slovenijo in slovenstvo. Obeležujemo ga s predavanji naših članic in članov ali uglednih gostov iz domovine in tujine. Zato mi je danes v posebno čast, da lahko napovem današnjega slavnostnega predavatelja, zaslužnega profesorja Dunajske univerze Antona Zeilingerja, ki si mu ob tej priložnosti zahvaljujem, da je sprejel naše vabilo. Profesor Zeilinger je eden od pionirjev kvantne fizike. Svoje največje in tudi najbolj odmevne rezultate je dosegel na področju kvantne informatike, kvantne kriptografije in kvantne teleportacije. Pred 2 letoma je za svoje raziskovalno delo prejel najbolj prestižno nagrado, ki jo lahko prejme znanstvenik, Nobelovo nagrado za fiziko. Delil si je še z 2 kolegoma za, citiram, poskuse za zapletenimi fotoni, ugotavljanje kršitev Belovih neenakosti in razvoj kvantne informacijske znanosti. Konec citata. Nobelova nagrada je seveda samo vrhunec številnih priznanj in nagrad, s katerim je bil počaščen profesor Zeilinger. Med drugim je prejemnik več častnih doktoratov in je član številnih akademij po svetu. Med njimi tudi naše. Slovenska akademija znanosti in umetnosti ga je za svojega dopisnega člana izvolila v letu 2023. Poleg znanstvenih dosežkov in sodelovanja s slovenskimi kolegi je bil eden od razlogov za njegovo izvolitev tudi poglobitev sodelovanja med SAZU in Avstrijsko akademijo znanosti, ki je profesor Zeilinger predsedoval med letoma 2013 in 2023 in za katerega lahko rečem, da je zelo uspešno. Danes, pred tem dogodkom, smo mu na manjši slovesnosti tudi izročili člansko diplomo in zato lahko rečem, da bo današnje slavnostno predavanje profesor Zeilingerja ob dnevu SAZU obenem tudi njegovo nastopno predavanje ob sprejemu v naše vrste. Naslov njegovega predavanja, ki bo seveda v angleščini, je Sporočila kvanta našemu dojemanju sveta. Naj tukaj še dodam, da smo se dogovorili, da bo po predavanju možno tudi, torej bomo imeli lahko tudi kratko diskusijo, če bo komu zanimalo, profesor je pripravljen odgovoriti na nekaj vprašanj. Dear Professor Zeilinger, it's my pleasure to greet you at the Slovenian Academy of Sciences and Arts. I would also like to thank you for accepting our invitation to give a festive lecture on the day of the Slovenian Academy of Sciences and Arts. In my address, I briefly remembered the beginnings of our academy, which we celebrate every year on November the 12th. And I also shortly introduced you as well. Now, I'm honored to invite you to share your lecture. Please, the floor is yours.
Thank you very much, President Stich, for your kind words. I'm sure they were kind. I didn't understand them. But I really appreciate and am very happy that I have become now a member of your academy, because for me personally, there are so many connections between Slovenia and Austria. And it's close to my heart that this can be even made better in the future. And whatever I can do for that, I will do it. So today I want to give you an overview. Maybe we can have the first slide. Well, do I have a pointer, or how does it work? Here's a pointer. Very good. And here is a pointer here. No, yeah, pointer. No, this is not the presentation yet. Okay. You know, there are only 5 buttons, and I never understand them all. But what can you do? Okay, you see there are some words in Slovenian. I hope it's correct. I want to today give a talk about the conceptual consequences of quantum theory, the way I see it. And I should warn you, this is a minority view. It's a minority view, but someday it will be the majority view. There's no question about that, of quantum physics. I have to show you a little physics, but not much. Now, I want to start with this picture. It shows Werner Heisenberg, who in 1925, when he was only 25 years old, discovered a new kind of physics, which he called matrix mechanics. It's the first version of quantum theory, and one of the popular essences is the so-called uncertainty relation, Heisenberg's uncertainty relation, written down in the first version I could find was this one, written in a paper by Heisenberg, which says P is the momentum, how fast the particle moves, like an electron, or maybe even this here, how fast it moves, and Q is the position where it is. And it's actually the uncertainty of the two. And the statement is that originally that you cannot know the position of a particle and the momentum, which is the speed, how it moves at the same time. It's not possible to take the two at the same time. So if you in your car, if you want to know precisely where you are, you better disconnect the speedometer, right? So you know the position. Now, the point is, this is an interesting history. Originally, this was thought to be a consequence of the disturbance, when you look at very small particles, the disturbance by observation. Because you have to look with light, something on it, and then you disturb it. The modern view is that it has nothing to do with disturbance, had nothing to do with observation. It's an intrinsic property. The particles themselves don't know where they are and how fast they move at the same time. There's an intrinsic limitation of nature, and not just our knowledge. So uncertainty does not know that I don't know, I am uncertain about something. It is I can't know. I can never know both. Uncertainty does not mean that I could be certain if I work precisely enough. So there have been actually experiments to try to look closer and to see whether we can beat this. The answer is clearly no. So there is no certainty. And that's actually one of, in my eyes, a deep philosophical consequence. Here is Erwin Schrödinger in 1925-26, Austrian Nobel Prize winner, who wrote down this equation. That is his handwriting. And below there is his grave in Alpbach in Tyrol. If you ever come to Alpbach, look up his grave. This is probably the technologically most important equation ever found by anybody. The whole modern technology rests on this. Semiconductors, for example, your mobile phone uses this thousands of times, and so on and so on. But Schrödinger worried, it says that, for him it said that you can understand the motion as waves. And he had a very vivid view of these waves propagating. The modern view today is give up any pictures you make for yourself. They only mislead you. The waves are just a way to talk about it, but not more than that. So where is my pointer? Here's my pointer. Here is my pointer. Here is my pointer. Now I want to discuss one of the basic phenomena, the so-called complementarity in the case of a two-slit experiment. This was very much in the discussion of Albert Einstein and Niels Bohr in the 1930s. They realized that the interpretation of the whole thing is an open question. Interpretation in the sense of what does it mean for our understanding. And just to explain a little bit what we are talking about here, there is here, where do I push? Here I push. These are two slit assemblies in the screen. You have to imagine that from the left you have light incident, and the slit is so small that the light is incident on these two slits afterwards. Okay, this is already a consequence of uncertainty. When you limit the size of your beam here, then the velocity in that direction is undefined. So it can illuminate both slits here. And then what happens afterwards? There are waves going through here, waves going through here in the picture. And then you say, oh, okay, the waves constructively interfere at some point, so there are bright stripes, the waves enforce each other, and there are dark stripes where the two waves coming from here, the one from here, the one from here, destroy each other. Okay? Now, Einstein realized already in 1905 that there's an interesting question. Namely, the question is, he proposed that particles consist of, that light consists of particles, really particles which spread around. Okay? Then he says, suppose I make the intensity so small. This is too advanced technology for me, this pointer. To make the intensity so small that only one particle at a time goes through, one particle of light. He says, isn't it natural to assume that, that the particle of light can go only through this slit or through this slit? Okay? Then if it goes through this slit, how should it know whether the other slit is opened or closed? Okay? Because only when both slits are open you get the fringes, the stripes. If only one is open, you don't get the stripes. Okay? So he predicted that if only one slit, if you make the intensity so low that only one at a time comes, and you have here a photographic plate which collects all the photons, you should not get any fringes. Now for that experiment he was disproven many times. Okay? Now some people say, and this is now sloppy language, which I find completely unjustified, they say the particle goes through both slits. This is, in my eyes, this sentence doesn't make any sense. The modern way to talk about this, is that we only get superposition of probability waves here, and we only get, important point is that we only get interference stripes when there's no information present anywhere in the universe which path the particle took. So it's information which is important. If there is no information, there's no possibility to find out which path it took, then you get the interference stripes. As long as there is a possibility to find out, and that is maybe on a star far away, you don't get them. So that's a strong indication that information is fundamentally important. We go on. The point now is that Einstein said, why did Einstein say? Einstein said that physics has to describe what is real. Then we had to describe which part it goes through, a real objective object like this here and so on. And Bohr said, no, science can only be about what can be said about the world. And I take, just to take it one step further, my position is that this does not only limit what we can say, but it also limits nature. Nothing exists about which not something can be said. Okay? This is the step I take, and we have to take it even more serious, I'm saying, than is usually done. So the old view was disturbance, the modern view is information limited. Here, just to show you some of experiments for fun. These are the stripes, intensity of neutrons, of Newton with neutrons at the reactor in Grenoble. These are the stripes, intensity stripes. And the point is that this picture was done with individual neutrons at the time. Later we did experiments with large molecules, also one at a time, and there is no limit. This is a very strong research field now to go to larger and larger objects, and someday maybe we can do it initially with master students, then with doctoral students, and maybe someday even with professors. That's of course how it could go. So the point is there is no limit at all. This is a nice experiment which I show for actually for your curiosity and to worry about. What we have here is my fingers are too big. The point is we have here a source, which creates pairs of photons, pairs of particles. One of the particles go through a double slit here, just the way you saw it before. And then you can get the double slit pattern. The other, the brother, goes through this lens or whatever, and goes through this lens, and then it can be detected in two different distances. If the detector is in one distance, then the particles which are detected together with with one here, they form the pattern. If it's at another distance, namely at a distance where using this you can find out where on the other side the particle went through, you get this pattern, no interference. So the point is that the phenomenon, whether this particle behaves here as a wave, the photon behaves as a wave or as a particle having a path, depends on decisions made after it has been detected. So there is no reality to the concept of path and wave. Depends on your decision what to measure. And then nature gives you some answer. So that's one of my favorite quotes from Niels Bohr. He said, no phenomenon is a phenomenon unless it is an observed phenomenon. And not only for us, also for nature. Now another important, so we talked about interference, we talked about the limits of information, and we talked about how information is fundamental and not reality. There's another famous statement by Albert Einstein in 1909 in Salzburg, where there was the annual meeting of the German Physical Society, and at that time the notion of German was not poisoned by nationalism or not on national socialism and so on and so on. So it was absolutely natural for Austrians to be part of the German Physical Society at that time. No nationalism implied. At that meeting in 1909, Albert Einstein expressed his discomfort about randomness. Namely, he said that he observed that the individual observation event, when you now discover a particle and you see it, that result is completely random. And he said that there is no cause. This was extremely far-sighted by Einstein, because the modern quantum theory by Heisenberg and Schrödinger has not been formulated yet. He must have had an immense intuition. He already said there is no cause. And this to me is one of the biggest discoveries of science in the 20th century. That we have cases where we claim there is no reason why this happens. It's just random. And it's not just our limited knowledge. It's a feature of nature that we have randomness. And that if you really think about this, that really changes the view of the world. The world is not as simply causal as many people think. It's not the way. Now, God wrote, then Einstein, in a very famous quote in the letter 1926 to Max Born, one of the founders of quantum mechanics, wrote that in any case, I am convinced that God does not play dice. He didn't like that. He didn't want it. He wanted a reality described, and not just, probabilities and information and all these vague concepts, To which, here we have a modern example how you can create, how you can see randomness. You have a source here, which puts out only one particle at a time. And you have a mirror here, which is, as we say, half silvered. So half of the light hitting the mirror is reflected here, half of the light goes through. This is so stupid. Half of the light goes through. I will now check if there's a bigger thing available for bigger fingers. Half of the light goes through. If you have a standard light come, you can see that when you stand in front of a shop, you often can see the things inside, and you can see a mirror image of yourself. Okay? Now, the question is, if I have a single particle here, I can do it with single particles. What happens? Does it be reflected? Does it go through? Will this detector say, click, I have it? Or, I need a secretary who hits the button. Will it reflect it, or will this detector click because it particle went through? The modern language is that after meeting the mirror, the particle is in a superposition of both possibilities. Just like in the double slit, after going through the double slit, the particle is in a superposition of both possibilities, namely having gone through here, going through there. It's wrong to say that the particle is in both positions. It's very you very often hear that from physicists, but it's wrong. So just the possibilities here, and then the individual thing is completely random. And we actually, on that principle, we built a random number generator. You can register this particle. One is 0, the other one is 1, and we wrote some CDs full of these random numbers and sent it to Siemens Corporation. They have a special division which is responsible for building good random number generators, because for some algorithms you need that. And they told us that is the best random sequence we have ever seen. We didn't tell them before that this was quantum. Afterwards we told them. Okay? So there's an application actually. Now, I told you that Einstein said God doesn't play dice, to which supposedly Niels Bohr told him, stop telling the Lord how to run the world. Well, Einstein was the only person who could try that. He was not successful in that case. He was simply wrong. Now so this was now randomness, which is a consequence of the fact that the information is not there where the particles go. It's fundamentally undecided. Now comes the thing for which I received, and my two colleagues received, the Nobel Prize. The situation is very simple. Einstein, with two other colleagues, that he was already at the Institute of Advanced Study in Princeton, said the following: I suppose I have two particles here, but just consider them as billiard balls who hit each other and fly apart. Then, according to quantum mechanics, they are always connected in the future. So whenever I do a measurement on this one, I get a random result, and the other one gives you the corresponding random result. So you have two random processes for which individually we know that there is no cause. But over large distance they give the same results. This is just crazy. Two processes which are completely random. This is completely random, no cause. We know that there is no cause. We can prove that. And here also. And they give the same result. And you do the experiment again, they give the same result, but now another result, and so on and so on. Okay? Einstein didn't like that. He said this is spooky. How could the other side know what happens here? Instantly, not with the speed of light. Instantly. And he wrote very nicely in 1947 to Max Born, the same letter I quoted before. I cannot believe in it, namely in this phenomenon, because that theory is then cannot be united or reconciled with the principle that physics has to describe a reality in space and time without spooky action at a distance. Einstein was wrong here. The person who immediately realized that something special is going on was Erwin Schrödinger, 1935. Immediately after the Einstein paper, he wrote a paper and he coined the notion Verschränkung or entanglement for the situation. I don't know what it means in Slovenian actually. I don't know. We can look it up. And he said, I would not call that, namely entanglement, one, but rather the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought. And my arrogant position is that the putting information as the fundamental object is the maximum departure you can have. Okay, so let's go on slowly. So the individual events are random, joint events are not random. Now there's the famous Schrödinger's cat example, which I have to show because everybody has heard about it and so on. This was invented by Schrödinger in 1935. This is the micro. Okay. The idea is very simple, but I want to go through it in detail because that's important. There's a radioactive a source, a radioactive particle, which can decay in a chamber. There is a hammer, there is a glass bottle with poison, and there's a cat. And the point is, in the beginning, the cat is happy and alive, but as soon as the radioactive particle decays and is registered by a detector, then the hammer falls down. Oops, sorry. The hammer falls down. The hammer falls down, and the poison is released, and the cat is dead. Now Schrödinger says, quantum mechanics says that the atom at any given time is in a superposition of decayed and not decayed. Therefore, if quantum mechanics is valid, the hammer would also be valid universally. The hammer would also be in a superposition of fallen down or not fallen down. And the cat, if quantum mechanics is also valid for the cat would be in a superposition of alive and dead. Now this has triggered many discussions. People talk about the cat being alive and dead and so on. This is to me not a sensible way to talk about it. The way to talk about it is that there is only the information. The information says that there's a possibility that this happens or this happens when I open the box. There's a probability for both of them, and that's it. The question whether the cat is alive or not before I open the box is a question which doesn't make any sense. Okay? So we go on. That this is the most elaborate equations I show you, but you don't have to look at them. You can look at them, but I don't have to explain. This is a source, how a real experiment is done. A source which creates pairs of photons which are polarized, polarization, horizontal or vertical polarized, and it creates many pairs, and they're always found to be either both horizontally or both vertically polarized. And John Bell, Irish physicist, in 1956? No, 65. Found out that if you assume that the two particles are born like identical twins, they have the same polarization from the beginning on. but randomly another one from one course to the next, then you cannot explain all correlations. You cannot explain all correlations. You cannot explain all correlations. So suddenly we have the way to test an idea, namely whether this picture can describe what goes on can describe in a realist local picture, namely assuming that the measurement results are given by realistically given by properties the particles carry here, and without instant communication, which is reasonable, because any communication is limited by the speed of light. That assumption doesn't work. The local realistic point of view doesn't work, and now we suddenly have the possibility to test a philosophical idea in experiment. And that was fantastic. The first experiment on this, Einstein locality simply means that if you have these entangled pairs of dice, there is no action on distance, and realism assumes that the world exists and we observers are only passive, that objects have properties without observation. Now, an entanglement, a possible application was quantum teleportation, but maybe I shouldn't go too much. How am I with time?
We are quarter to 12 now.
Sorry, quarter to 12 now. Thank you. Okay. Now this is the idea of quantum teleportation, which is an application of entanglement. Quantum teleportation. This made big news. It was actually interesting. When we did this experiment in Innsbruck, 1998, we published it. And the first thing is we sent the paper to, I want to tell you that because this is really curious. We sent the paper about experimental quantum teleportation to Nature, very prestigious journal, and I didn't hear anything from them. So after 2 months, I called the editor of Nature, what's going on? And I heard her on the phone, Apparently they hadn't done anything. They didn't know what to do of the crazy title. And then I heard from a famous quantum physicist in London. This was before the internet, actually. Before you could send big files and so on. The Nature called him and told him, we send you now a manuscript by motorbike, and all we want you to tell us, is this serious physics or not? And he said, okay. That's funny, really funny. And anyway, so the point is that what does entanglement mean again? If you have here an entangled pair, which you produce in a suitable kind of source, it means actually you create the pair such that none of the particles has its individual properties well defined. They don't know who they are. If they were identical twins, they don't know who they are. But they know that if I am measured, my result will be random and the result of my friend will be the same. So what we do now is we take an initial state, initial photon in our case, which we want to teleport. We want to teleport its state. And here we use additional entangled pair. And then as we say, we project the two onto an entangled state. So we can project the two on the entangled state, which means we erase their individual properties. But we can get the information, for example, the two are the same, without learning what their properties are. But we just get out here the information the two are the same. Since the two here have to be the same, by simple logic, this is the same as this is the same as this, therefore this one, therefore this one is the same as this. And the original has lost its individuality. So it was teleported over this distance here. Now the point is that there can be different kinds of entanglement, and therefore there is classical information, but this is not very important. This here was the experiment which we did a while ago. In principle, I don't want to go into details, but in principle it looks very simple. Not many optical components. A number of experiments now have many more optical components. Very, 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 very simple experiment. Unfortunately, we did not keep the setup because now some museums have been asked for it, but it doesn't exist anymore. The components have been used for something else. Now, just to give you a picture here, we do experiments over long distances. A beautiful series of experiments we did over between the Canary Islands of La Palma and Tenerife. We produce the pair here, measure one locally, the other one goes over there. We can establish entanglement over large distances. Our Chinese friends established entanglement with the satellites over large distances and so on. And all this entanglement can now be used via teleportation to connect different quantum computers, if they ever should really exist. I mean, the news shall write all kinds of things what is achieved, but quantum computation is a very interesting field. Many people are working on it, but the problem is that nobody dares to say that we will have it before 20 years from now. It reminds me a little bit of fusion. When I was studying physicist, fusion was 20 years ago, ahead. Now fusion is 30 years ahead. Cold fusion, for reactors. But never know. You never know. But the research in quantum computation is fantastic. People just shouldn't try to sell it as an immediate application. Now we did one of the most crazy experiments, and to me, from the setup, most fantastic experiment was an experiment we did again on the Canary Islands, where we created a pair of particles, send one here, send one here. And then you have big telescopes. These are telescopes in the 4-meter class, which is a substantial size for a telescope. This one is operated by our English friends, William Herschel telescope, and this one, the Telescopio Nazionale Galileo, is operated by our Italian experiment. And each one looked out independently. It was the first time in history that the two telescopes were used for the same experiment. Each one looked out very far to objects which are very, very far away. So you get information from very early in the universe. They looked out to quasars, quasi-stellar objects, away at a distance of the order of 8 to 12 billion light years. The reason was that we wanted to measure, to decide what to measure on the two entangled photons as independent as possible, such that the decision what is measured here cannot be known on the other side, and vice versa. And for that, we took these quasars. We took light fluctuations of the quasars here to measure the polarization here. Lo and behold, we got a violation of Bell inequality, so we confirmed non-locality. I tell you, when you see on William Herschel telescope, we saw on the monitor light from a quasar 12 billion years ago. That is really something. When you see light which came so far from the universe, it changes your view a little bit. At least it changed my view a little bit. Anyway, I think I should keep this. Now I come to the conceptual part, more conceptual than we had here. There's a beautiful statement in 1985, 100 years of the birth of Niels Bohr in Cambridge, Massachusetts. They all talked about all the big shots sitting out there. I was a young guy. Oh, well, I was already 40 years old. Well, Anyway, but I was certainly young and unimportant. And I was sitting in the back row, and there were all the big shots sitting out there and all saying how well we understand everything and so on. And suddenly in the first row, a little old man gets up and says, I think we are missing a very basic point. The next generation, when they found it, will knock on their heads and say, how could they have missed that? And sits down again. There was a minute of embarrassment, and then the discussion went on the usual way. So I walked up, I didn't know the guy. I walked up to him after the talk and introduced myself, and I found out that this was Isidor Rabi, the inventor of nuclear magnetic resonance. You know, all the nuclear scans and all this is based on his invention. So he was somebody. He was not just a silly guy. A basic point. How could they have missed that? And it's the role of information. There's also a beautiful quote by Niels Bohr. He said, I told you already the role of information. He said there is no quantum world. There is only an abstract theoretical quantum physical description. It is wrong that the task of physics is to find out how nature is. Physics concerns what we can say about nature. And I take this one step further. I take this one step further. My position is that information is a fundamental constituent not of just what we can know, but of the universe. The most basic constituent of the universe is information. Information is defined as a possibility to make a distinction. It rains, yes or no. The possibility to make a distinction is information. Who makes the distinction is completely irrelevant. It's also irrelevant whether the distinction is made by somebody. It's the possibility. Now there's also one guide for me was this statement by Bohr, where he said, however far the quantum phenomena transcend the scope of classical physics explanation, the account of all evidence must be expressed in classical terms, must be expressed in language. And therefore, this is my sentence, quantum states are only the representation of classical information, the knowledge of my apparatus, which laser is there, which mirror is there, which kind of lens are you using, and so on. Classical information in a quantum formalism. So the quantum state is just a representation of information. Information about what? Information about results of observation and the pieces of apparatus and so on. Classical information. You can see that. You can see it printed out on a paper. Okay? Information what for? To calculate probabilities of future events. I told you we have randomness. We have only probabilities. Namely future features of classical apparatus. And forget properties, quantum properties of particles. And I claim there is no more. I told you that this is a minority view. Not everybody subscribes to that. You know, there's a famous measurement problem. The measurement problem means when you think back of Schrödinger's cat. The cat is in a superposition and people worry, then how does it happen? What is the process which makes it happen that the cat is, when I look at it, is dead, or the cat is alive when I look at it? Okay? And my claim is there is no measurement problem. Now this is a big problem that I say that because a large part of the physics community has spent their careers on solving the measurement problem. And I suddenly say, no, there is no problem. Okay? Why? And if we talk about representation of our knowledge in the quantum system, then isn't it most natural to change our representation of information, namely the quantum state, when our knowledge changes because of new information? I open the box, get new information, I have to change the representation of my knowledge. There is nothing to be said about what was really going on before. Nothing at all. Okay? There's a beautiful quote by Heisenberg, 1960. The act of recording, namely measuring, is not a physical, but rather, so to say, a mathematical process. With a sudden change of our knowledge, also the mathematical representation of our knowledge undergoes, of course, a sudden change. And that's it. There is no more to it. Now I come to my last slide. The real question now is, why do we have quantum physics? This is a step further. Why do we have quantum physics? Not just because we have these beautiful equations and everything we predict coincides with what we observe, but why, in the sense, when you, for example, think of Einstein's relativity theories, the special relativity theory is built on a very simple principle, namely the fact you cannot distinguish whether you are in an accelerator, like an elevator which is accelerating, or whether this is the gravitational field. You cannot distinguish that. This is most natural. And Einstein said, physics shouldn't make a distinction between the two. Okay? No, this is for the general theory. For the special theory, it's just the question you cannot distinguish between continually moving different systems with different velocity. Now there is interesting. There is, I think, a word is. Here it is. Now this was introduced once many years ago by a student of mine. That this comes in like that, you know, and I cannot get rid of it. It always comes in. There was supposedly a famous discussion by Bohr and Einstein, which was actually registered by Abraham Pais. You know, the two were working, and they looked up at the moon, and Einstein asks Bohr, do you really believe that the moon is not there when nobody looks? And Bohr said, can you prove the contrary? Now, here are just the thing which also tell you what I'm working now on. To me, information is the most basic concept, Ursubstanz, Urstoff of the universe. And now it comes. Information is always expressed in classical language, a statement in language. Now the point is that the statements are countable. You can count every statement, 1, 2, 3, 4, but just assigning values to the individual letters and so on. This is just what Kurt Gödel, the most famous logician, whoever did, used in his proof of Gödel's theorem, namely that mathematics is by necessity incomplete if it's sufficiently complex. Now statements are countable and therefore quantized. So the structure of quantum mechanics follows from the fact that it is about statements we can make. And in the end, I just would like to quote famous thing, the beginning of the Gospel according to John, in principio erat verbum. Maybe a circle closes here. I want to conclude with two somewhat funny quotes. This is from 1913. Einstein was professor at the Eidgenössisch Technische Hochschule in Zürich, And Berlin wanted to get him to the academy. Apparently the academy was able to hire people and give them a good salary. Okay? And there was a letter, this is actually really funny. So they proposed Einstein with a good salary. Supposedly this was a very good salary. I don't know, in the beginning 6,000 mark and later 12,000 mark. And then they say, the fact that in his speculations he occasionally shot beyond the goal, for example, in his hypothesis of light quanta of light should not be held too strongly against him. Because without occasionally taking risks, even in the most exact scientists, you cannot introduce something really new. Now we smile about that. This was in 1905, Einstein has proposed the idea of particles of light. This was in 1913. And the signature, this contains 3 Nobel Prize winners. And the third one who not got the Nobel Prize was Rubens. But he had done the early experiments which led to blackbody radiation, quantum mechanics and so on. Now we smile about it. But they had reasons to believe it. But now, what I really like is Einstein got the Nobel Prize of 1922 just for that, not for relativity theory. And that's so fantastic about science, that the whole worldwide community can change its mind because of evidence. Nature says, no, you guys are wrong. And they accept it. Now this is my last slide, famous slide by Einstein, written towards the end of his life. I want to know how God created this world. I'm not interested in this or that phenomenon. I want to know his thoughts. The rest are details. Thank you for your attention.
Thank you for this interesting lecture, after which, as a completely outsider, I can say that there is a lot of philosophy in physics.
You know, there was actually there was actually some statement in the 1920s by somebody complaining that there is not much going on in philosophy, and somebody answered, yes it is, but the philosophers are now sitting in physics departments. I hope this doesn't offend any philosopher here. I hope.
Okay, thank you very much, and now the professor is prepared to take up to 3 questions, please.
But wait for the mic, maybe. You know, a widespread phenomenon is that they discover that the batteries are out in such microphones. No, bitte.
You had one slide where you said that already in 1909 Albert Einstein was uncomfortable with randomness. What was the occasion for that already at this early stage?
I forgot. One should look it up. It was not a paper he presented, but it was in a discussion section. I forgot what his reason was. I read it many years ago. Maybe it is a good point that I should look it up again. Thank you. Thank you.
Do you remember exactly what was the reason that Rabbi made the statement?
No.
I mean, since you were there.
Unfortunately, he only said this short sentence, and unfortunately, I was the only one who talked to him afterwards. Unfortunately, I was a very young guy with very much respect, I didn't dare to ask him what the reason was. I should have. You are right. I should have asked him. But I've written it down in my notebook, so the notebook still exists. So there's some proof for that. It's not just fantasy.
Thank you for a very nice lecture. I just have a question. Do you have an opinion on quantum gravity?
Yes.
Can you share it?
Yes. This is very important. The unification of quantum physics and gravity. To me, and I'm not joking now, I really mean it, that some of the top physicists who ever lived, which means some of the probably most intelligent members of our species, Homo sapiens, have worked on this now for 100 years. And we don't have a real result. We have different approaches and so on. We don't have a real result. In my eyes, this tells us that we are just searching in the wrong direction. The Americans have a saying that we are barking up the wrong tree. When the dog is on the tree and the cat is out there, the dog still barks up the tree, but the cat is already somewhere else. I really think that some very fundamental new view at the situation is necessary. That is my personal opinion. It's an opinion. I cannot prove it.
I come from the field of Bible studies, and in this connection of the history of language, we have in the Bible very good example, the book of Job, who cannot accept the phenomenon of the world with suffering. And then he gets about 100 questions how he could explain any phenomenon in the physical world. And because he cannot find answer to any of 100 questions, in the end, he does no more put any questions, but decide that he will only listen to the word of God, and in the end he finds his inner peace. Now the question is how to explain the relationship between what in German is said Begriff und Metapher, concept and metaphor. Anything connected with the language expresses only phenomenon, not Ding an sich. And from this point, we could ask whether in physics there is any chance to begin what will be in the next generation more important, the interaction between physics and humanity or humanistics.
The interaction between philosophy and physics is extremely important because in quite some situations we need new concepts, and the new concepts cannot come out of the existing physics. They must come out from some analysis of what science is, what we can say. I mean, it's just like Ernst Mach's analysis of space and time apparently was important for Einstein. And we now, in the 21st century, we suffer from a widespread separation between philosophy and physics and science, and this is not good. I had some connections with philosophers. I had invited them But I found out that my philosophy friends were more conservative in keeping the worldview than we physicists. It's very interesting. So there is something interesting. But since you mentioned, the questions and so on, this randomness we have in quantum mechanics is really the maximum ignorance you can have in the situation. And I try to say provocatively that even God does not know what the outcome of a quantum experiment will be. And then I had a discussion with a cardinal. I invited him to my group and we discussed and so on, and he was not so happy about my statement. So I told them, I asked him, what does give us the right to limit the powers of God? And he said, what do you mean? Why should God not have created the world such that there are things which will surprise him?
Nice words to conclude. Thank you very much.
Thank you. Thank you. So very good.